Hello, everyone. We're finally back after some well-deserved summer vacations. We hope that everyone was able to recharge, finish their dissertations, and get ready for the next season. We have prepared a very interesting series of talks for the upcoming months, so you guys stay tuned. Today with me, I have my colleagues, Marcel Mora from the University of Oslo, Nara Brandao from the University of Uberlandia in Brazil, and Mohammed from the University of Oslo. Hi, Mohammed. Today, we have two really interesting talks from two great speakers. We have Carlos and Hasan. And without further ado, I'm going to introduce Carlos. He will be presenting fractal modeling techniques for predicting production in unconventional reservoirs. So Carlos Silva Escalante is a PhD student in reservoir engineering at the National University in Mexico. He is a petroleum engineer by training, and his research has been focused on optimization of production, unconventional reservoirs, and reservoir simulations, and of course, fractals. So we are looking forward to this very interesting talk. And Carlos, please take it away.
Hello everyone, my name is Carlos and I will talk you about fractal distribution within simulation models with logarithmic space. Scopes of this work are two: to model the fractal behavior in stimulated reservoir volume SRV within a commercial reservoir simulator which doesn't perform this technique, and to analyze the production behavior within the fractal model proposed in this work. Then, as introduction, the stimulated reservoir volume is an important part of the reservoir and study. Its geometry is function of petrophysics properties, fracturing configuration, and pre-existing natural fractures. This work we considered three types of SRV: a local SRV, where the stimulated zone surround the main hydraulic fractures without contacting with the neighbor fracture stage. Then the second is the regional SRV with stimulation zone among fracture stage completely. And the third uniform SRV is the commercial use, and consider and uniform natural fractures properties in whole reservoir model, and there are several opportunities areas consider this case. Then one note, local and regional SRV provides an unstimulated reservoir volume URV. The first media fractal distribution, PMFD, has a fractal dimension less than Euclidean dimension and is considered within the permeability and porosity of the natural fractures. Euclidean D is a fractal special case where the fractal dimension is the same of Euclidean, and it can be 1, 2, or 3 depending of the flow dimension. Chang and Georsos consider two equations governed by power law, like this, where theta is the natural fractures connectivity. When theta is 0, we consider fully connected in the natural fractures. When the theta is 1, we consider the natural fractures totally isolated. And where L is the main length of SRV among the fracture stage. So index 0 is the tangent value in front of the fracture phase, is the first value. and theta, the natural fractures connectivity. The next slide, we can see two SRB types. In the left, we have the local SRB. These blue planes are the hydraulic fractures. And these blue lines, represent the natural fractures. And we can this behavior to the isolated zone between hydraulic fractures. Then, if we have this case, we consider this behavior of the permeability and porosity of the natural fractures, just in this case. Then, if we consider these totally connected natural fractures, we have this power law behavior. And with this, thanks for the box counted method, it's just one method of, I think there are three, to approximate the fractal dimension in the reservoir. This with put a grid over the core face, increasing the number of boxes, and we count the number of boxes with natural fractures, and we plotting this way. The slope is the same of the fractal dimension. R is the number of the boxes, and function of R is the number of natural fractures. The first model is the conventional in commercial simulators, and the A model is Euclidean. Then the fractal dimension is the same of the Euclidean as one because we consider just one dimension flow between this part of reservoir to hydraulic fractures. This model has uniform SRB and no fractal, and homogeneous natural fractures properties in the whole reservoir. This is the well, and these are the hydraulic fractures, and all blue zone in this image is the homogeneous natural fractures properties. Then the behavior of the permeability and porosity is this way. The second model is fractal. Then the fractal dimension is between 1 to 0. Then theta is the same. The fractal is local over here, and we have this behavior. The red colors indicates the maximum values, and the blue the minimum. Then we can observe how this behavior can be representing this model over this model. Then we consider 2 points. The matrix permeability is less than the natural fractures permeability over the URB, this point, and both less than natural fractures permeability over the SRB. Then similarly with the porosity, the natural fractures porosity over URB is less than the natural fractures porosity over the SRB, and both less than the matrix porosity. Then the third model is this FR model. It's fractal, has regional SRB, it's like this. Then the URB is a round of the SRB. Then if we we can see the colors and we can interpret this behavior like this. Cleanly, power law governed behavior. The point is the same as FL model. This is the well, hydraulic fractures, and the SRB. Then results, production matching among models. This image, we can see the history data in red points and the base case in the black line. We can see how the FR model and the Euclidean can matching in the early times and late times, and the FL model just in late times. But if we compare the Euclidean and FR model, we can consider that Euclidean can give us some mistakes in results or errata in data. Then if we compare these results in the A model, we have less values in the hydraulic fracture permeability comparing with the FR model and FL. And one advantage of these fractal models is the results in the URP, like this. Then we can compare or corroborate with the laboratory results and increase the knowledge about what reservoir we have, what type of reservoir we have, and its properties. Then other results is a fractal parameter sensitivity. In the black line, we have a Euclidean behavior with fractal dimension as 1 and theta 0, considering totally natural fractures connect. Then if we decrease the fractal dimension like 0.7, we have the blue line, and if we decrease more, we have the red line with 0.4. Then if we want decrease in the theta, we have the pink and the green. The green indicates the totally isolated natural fractures. And in all cases, we have underestimate production. It's important. And conclusions. The parameter with greatest impact is theta. However, change in fractal parameters affect the reservoir production. The fractal model can be approximated to real behavior, and we can know the geometry and properties within of SRV, stimulated reservoir volume, and unstimulated reservoir volume. This ain't possible in conventional modeling. And it's possible to obtain a discretized porous media fractal distribution within the grid nodes with logarithmic space, and shows an improvement area for future sophisticated works in reservoir simulation. Then my reference, and it's all for me. Thank you.
Mic was muted. Thank you very much, Carlos. That was a very interesting presentation. If we have any questions from the audience, please feel free to type them in the comments. And I have one myself. So, Carlos, this the fractal dimensions that you measure, they rely on the box counting method, right? And this one, it's you need to have a full image of the fractal structure to do the box counting on top of it, I guess. So I'm wondering, in experimental images, if you have like CT data or in micromodeling or anything like this, do you know if there is enough resolution with the current techniques to actually extract this kind of fractal dimension using box counting? Do you have this information from the experiments nowadays?
Yes, if you have several data of information, and you can obtain more precisely in the fractal dimension. If you don't, well, the box counting is an easy tool to understand, and only with visible natural fractals you can approximate a fractal dimension. But if you have a history matched with the data production, and the fractal dimension can be a parameter of sensitivity. Then the characterization results gives us a fractal dimension as a parameter like the porosity or permeability. Then is useful techniques, but with the commercial simulators, don't have the fractal dimension as parameter in the history matching. Then it's hard. But there are several methods also for determining the fractal dimension, like deterministic methods and logging, I think.
Carlos, very interesting presentation. I have another question kind of related to Marcel's. Do you think that different areas in the reservoir are going to have a different fractal dimension characterizing the fractures? Or do you think it's okay to assign one for the entire play of interest?
Can you repeat?
Yeah, so my question is, do you think that the fractal dimension changes along the reservoir, or
of course, the fractal dimension can be varied along the reservoir. It is depending of the scales. Then it is important issue to study, but several parameters can depending of scale. Then more in the unconventional reservoirs, because they have several heterogeneities along the shale, and of course the fractal parameters as others can be varying along the reservoir.
All right, so I think we don't have any other questions, right, on the chat now? I think we don't. So let's thank Carlos very much. Thank you for a very nice presentation. And then we can move on to our next speaker of the day, and this will be Hasan. So Hasan Khan, he's a postdoctoral researcher associate at the Department of Geology at the University of Illinois at Urbana-Champaign. He received his bachelor's in petroleum engineering from the NED University in Pakistan and a master's and a PhD in petroleum engineering from the University of Texas at Austin. Currently, he's working on characterizing physical-chemical alterations of the shale matrix and fracture evolution due to the injection of hydraulic fracturing fluid. So Hasan will be talking about this to us today, and I'll leave you the floor so you can share your screen. Hasan, I think you have it there, right?
So can you see the screen, Marcel?
We do, yes.
Awesome. So hi, everyone. My name is Hasan Khan. I work as a postdoc at the University of Illinois. The topic I present today is concurrent solubilization and fines migration in fractured shale during acid injection. This work has been worked under collaboration with Dr. Cynthia Ross and Dr. Jennifer Duhan. So I'll start this presentation by talking a little bit about a recent review paper that we published, in which we review the relevant transport and geochemical properties of shale. Specifically, we focus on 5 mechanisms via which we see temporal and spatial evolution of the fractures. This includes shale softening, mineral precipitation, wettability alteration, fines migration, and mineral dissolution. So in shales, there are other mechanisms, such as mechanical mechanisms, such as compaction and creep, that also are very important parameters. But for my work, and specifically for this work, we are interested in the geochemical properties of the rock. Some work in this regard has been performed at the SLAC National Laboratory in California. They took out 2 samples, 2 different types of shales, a carbonate-rich Eagle Ford and a carbonate-poor Marcellus shale, that they exposed to an acidic brine for a period of up to 3 weeks, after which they cleaned out the sample, sliced it in half, and conducted micro XRF on the surface. Based on those studies, they were able to generate elemental maps, which are presented on the bottom right-hand side. And a distinct thing that they observed was that the carbonate content governed the depth of the reaction penetration. So in the Marcellus shale, which had a lower carbonate content, you could see that the acidic fluid penetrated deeper inside the rock as compared to the Eagle Ford, which had a higher carbonate content. And this, again, is a little bit expected, because the higher soluble minerals we have, the more amount of fluid it would require to neutralize. Therefore, less of the reactive fluid would penetrate deeper inside the rock. So continuing along the same thought process and applying it to the real hydraulic fracturing operation, the next important parameter that we would want to include is advection, because it is a very important parameter in hydraulic fracturing. So in this work, we're trying to study, like, how does advection affect the depth of the reactive fluid penetration. For this work, I am working with the HFTS core samples. They are taken out from the Wolfcamp Formation in the Permian Basin at a depth of about 9,277 feet. The sample that has been chosen has a carbonate content of approximately 10%, and this value lies in the middle of the carbonate in of the Marcellus and Eagle Ford samples that I showed previously. Once we identified the sample, the next step was to generate an equilibrated brine, for which we reworked the produced water chemistry, and working under the properties of under charge balance, we were able to draw or generate a brine recipe. And we created that recipe, tested it out by exposing a piece of shale to that fluid sample and periodically collecting fluid samples from it. And based on those fluid samples, we were able to analyze them and look at the major cations, from which we determined that since the major cations are not altering, we can deduce that the fluid is equilibrated. And this is the fluid that we have been using in our experiments. So the general outline of the experiment is below. So initially, we have a shale sample that we fracture with a Brazilian test. Then we conduct a baseline CT scan, which would give us a fracture network and the fracture orientation. Then we expose the rock to the reactive fluid, after which we conduct a post-flood micro CT scan. And the difference between these 2 CT scans would give us the change in the fracture aperture, like how the fracture aperture evolves due to the acid injection. And we reiterate this process until we have the desired amount of fluid pumped through. Finally, we conduct SCM and EDS on the fracture surface. And from that, we are able to generate the elemental map as well as the surface structural map. So the sample was a Wolfram sample. It was a small disk. We conducted a Brazilian test on it. Unfortunately for us, the fracture was created that was parallel to the phase that is shown here. So something like this, the orange phase. So we had to redraw or remake the sample such that we could flow the fluid through the generated fracture. So we reworked the sample by putting epoxy on the sides, and in the process we also add fiduciary markers. These markers are later utilized for image alignment. So once we created the sample, we conducted a baseline micro CT on that using the X5000 industrial CT scanner that is located at the Institute of Genomic Biology at UIUC at a resolution of 11.6 microns. The bottom right-hand side shows a reconstruction of the fracture surface, and top left-hand side is where the fluid is injected, or that is the inlet phase. Using image analysis, we were able to identify and measure the fracture volume, which is 0.283 cubic centimeters. For our experiment, we selected a flow rate of 0.01 milliliters per minute, and this was selected such that we have a high Peclet number and a laminar flow, something that is common in the hydraulic fracturing operation on the Poor scale. The schematic of the experiment is shown on the right-hand side. The core is connected to two syringe pumps via a three-way valve. Initially, the equilibrated brine is injected inside the core until the core has been completely saturated. Then the switch is flipped, and the nitrogen-sparged acidic brine is injected inside the core. Once the desired amount of fluid has been injected, we then again switch the valve and re-inject the equilibrated brine so that we can push out or flush the acidic brine out of the sample. Once we're fairly confident of that, we flush out the sample with nitrogen gas and take the sample to the micro CT scanner for scanning. And so the total flooding time we have selected is 32 hours, and we have broken it down into 3 time steps. So the reason behind that is this way, once we will have 3 different CT maps at different time steps, and so that we can see how the fracture evolves over time. Combining the results, aligning first, the images are aligned, then the fracture maps are generated, and the differences between the fracture maps give us the change in the fracture aperture as well as the fracture volume. So over the course of our experiment, we see that there has been a 16% change in the total fracture volume, with most of the change happening in near the inlet. Again, this is a little bit expected because at the inlet, the reactive fluid or the acidic fluid has the highest efficacy, and as it progresses inside the rock, it neutralizes and loses its efficacy. The fracture area per unit slice is plotted along the length on the bottom right-hand side, and this has been plotted on a relative scale. So, for example, the red line indicates the change in the fracture area between the baseline scan and the first flood. Then the dotted line, blue line, represents the change in the fracture aperture between the second scan and the first scan, and so on and so forth. So we see that there are different mechanisms happening. We can see in some regions that we have the fracture that is widening or opening up, and in some instances we see that the fracture is narrowing. And we can attribute the widening to either mineral dissolution or fines migration, and fracture narrowing to either mineral precipitation or fines entrapment. The first flood is again plotted on the right-hand side. In this, we can see that in different lengths, depths inside the rock, we can see either fracture widening or fracture narrowing happening. And most of this has been happening, or most of the change has been happening in the near inlet phase. So once the CT scans have been conducted, the next step is to dry out the sample and then conduct SEM scans. For this, we cut out the core, we open it along the fracture face, and then slice it along the cutting plane. So this exposes two phases. The first phase is the fracture phase, that is where the fluid was flowing through during the experiment. The second phase is the profile phase, that is the depth inside the rock away from the fracture surface, that is orthogonal to the fracture surface. So we polished the surface and coated it with silver, so coated it with gold prior to the SEM, and for the fracture surface, we just coated it with the gold particles, and we did not polish the surface because we wanted to capture the surface topography. So looking at the fracture phase, we were able to see some really cool features. For example, in this image, we can see like the organic matter and pyrite clusters as well as some feldspar. Similarly, if we look at the profile phase, we are able to identify other minerals as well as organic matter in this case, like calcite, dolomite, pyrite. All of these are pretty evident. But looking again on the fracture surface, specifically near the inlet where the fluid is moving in, when we look at the elemental maps, one thing that stands out clearly is that the response on the calcium map is very low, which implies that the calcium has been dissolved out on the fracture surface during the flooding process. And if we look closely on the backscatter images, like zooming in on this part, we can see, for example, here that a dolomite rhomb used to exist here, which has been completely dissolved out during the acid flood. When moving on to the profile phase, the first thing that stands out is that we have a lot of microfractures that are parallel to the fracture surface. And again, this is expected because once we were doing the Brazilian test, there were fractures that were created that are a little bit evident in the micro CT, but a lot of them are sub-resolution that are more prominent in the SEM scans. An interesting aspect here is that at the inlet, we see a larger aperture microfractures as compared to the outlet where we have smaller apertures. Looking at the elemental maps in the profile phase, what we observe is that the calcium map is pretty uniform. We don't see a significant loss of calcium, anything similar to what we observed on the fracture phase. So again, just to reiterate, the yellow dotted line here is the fracture surface. And if we're moving on the left-hand side, this is the depth inside the rock, that is away from the fluid that was flowing on the rock surface. So we see, based on these, that there was no discernible loss of calcium away from the fracture surface at the inlet. Similarly, we measured the characteristics at the outlet, and similar results. We don't see a discernible loss of calcium away from the fracture surface in this instance as well. So combining up the results that we have seen, we see three major results. Firstly, we see that the fracture aperture increases during the core flood experiment by as much as 16%. We see evidence of calcium dissolution on the fracture surface based on the elemental maps, as well as examples of dissolution patterns, such as like a dolomitic rhomb being completely dissolved. And thirdly, when we look at the profile phase, we see that there is a minimal loss of calcium away from the fracture surface. So when we combine all of these up, the thing that it points to is that we see a physical loss of rock, which means that we are eroding fines from the surface, or we're removing rock from the surface. We propose a mechanism via which this is happening. This mechanism is dissolution-induced fines migration. The idea is that we have a fracture aperture, H1, through which the acidic fluid is initially flowing. As time progresses, the reactive fluid interacts with the matrix and dissolves it out, resulting in weakening of the matrix. And as more and more fluid passes through, the weaker matrix erodes, and that exposes fresh rock surface. And that basically restarts the process, because this fresh surface interacts with the fresh fluid that is coming in from the left-hand side. And this results in an even further increment in the fracture aperture. And the new fracture aperture H2 is larger than the older fracture aperture H1. So we have recently submitted this work along with some modeling work to the Fuel Journal by Elsevier, and we're hoping that we would be published soon. Thank you very much for listening to my presentation. I would like to, this work was performed as part of the Center of Mechanistic Control, which is an Energy Frontier Center funded by the DOE. Part of this scanning imaging was performed at the Stanford Nanosheet facilities, as well as the Institute of Genomic Biology at UIUC. And finally, I would like to thank the Porous Media Tea Time Talk team for inviting me to this session. Thank you very much, and I'm open for questions now.
It's our pleasure, Hasan. Thank you very much for your very nice talk.
Thank you.
So I have a quick question to start myself. Although if there is any question from the audience, please feel free to type it in on the comment section. So show the fracture surface as a function of position along the length of the sample, right? There is one of the plots that you've shown. And then there is a bump in the beginning. And this, so you said that this is likely to be because the fluid is more reactive, right? It's more concentrated, the reactants there.
Right.
And then there's a bump at the end also. Do you know how to explain the bump at the end?
So just let me go back. So looking at the baseline scan, that is the red one here, the initial one shows the total fracture area. So if we look at the fracture that was generated, for example, here, this is the top end. So we can see two fractures that were initially created. And the way the structure of the fracture is oriented is that these two fractures meet up in the middle, and then it goes away, and at the end, it diverges again. So the red line where it shows the bump initially, this is the region where the two fractures are independent. And then when they converge, they sort of form to a uniform length again. So this is what it's implying. Like the initial bump is that there are two independent fractures that meet up in the middle. Then as we move towards the end, they diverge again. So that's why we're seeing an increase. The reason where I say that we see a more prominent change in the fracture aperture near the inlet is that if we look at all the subsequent scans, we see that the highest change is observed near the inlet. So if you transition from the red line to the blue line, most of the change is observed here. We see a significant change here as well, but most of the value has been changed in this part. So that's what I was trying to get across.
Great, thanks. Do we have any other questions in the studio?
I have one question. Hasan, now that we know this, how can we use this information? Can we upscale this? Can we inform the subsequent scales? What's your take on this?
That is actually the idea. So if this thing is true on the reservoir scale, then it changes. Like right now, there is a lot of talk about, and people have been reusing a lot of produced water as part of the base fluid for the hydraulic fracturing fluid. So if this case is true, then we would have more issues with regards to the fractures when we're using a produced fluid that has more salt content in it, because if we have a higher salt content, then the dissolution would reduce. If the dissolution reduces, the fractures does not get as big as we are expecting. So that is sort of impeding the fracture growth. So this is something like we need further studies for that, specifically at reservoir scale, as well as like at higher pressures and temperatures. Right now, these studies were conducted at ambient pressures and temperatures. So if we do these studies again at higher pressures, where we have a compressive force, we would probably see a different response, because in that case, the fracture, the weakened part would be under a lot of compressive stresses that will force it to close, and which might either result in reducing the fracture aperture further, or it might even cause a higher chipping or erosion to happen, resulting in a higher aperture. So this is something like this is work that is currently underway.
Okay, nice, Hasan. And please, I also have another question that you mentioned that the the fractures generation depends on the acid concentration and the mineralogic composition of the rock. But which other experimental parameters do you think also influence the fracture generation and propagation?
If we're talking about from the geochemical perspective, like there are mechanical perspective in which compressive stresses play an important part. But if you're talking about the chemical reaction point of view, the acid concentration, or specifically the pH, plays an important part. The velocity plays a very important part. So if you're injecting more and more fluid, for example, if you're injecting fluid at a specific rate from the left-hand side, that implies that fresh fluid is coming in at a specific rate. If we increase that flow rate, like double it up, that means 2 times the fluid is moving past this part of the rock, which means like the rock is now exposed to twice the amount of fresh fluid. So the amount of reaction increases, and therefore the fracture growth changes at that point.
Okay, great.
All right, so I think if there are no further questions, we can wrap up the session and thank once again both our speakers from today, Carlos and Hasan. Thank you for joining on our very first session after the summer break. We are still slowly getting up again to the rhythm. And do we have the closing slides there? Ara? Yes, super. So we are going to get back on 2 weeks from now, on the 7th of September. And this session will be earlier, so that will be at 10:30 Central European Summer Time. So we try to change the times so that we can fit different time zones around the globe. And now we have 2 speakers, Ishan Markal from ETH Zurich and Yu Ying from Sydney, from the University of New South Wales in Australia, not Sydney, Australia. And that will be at 7:30 on the 7th of September. So we hope to see you there. Thank you once again for joining us today, and see you in 2 weeks. Bye-bye.